of all, I apologize that the website might have some issues because there's too many people signing up at the same time. The engineering team is working on it as of right now. I just texted them, and they just texted me saying that, oh, there's just too many people signing up at the same time. So we'll see how it goes. If it doesn't work, I'll just ask you questions, and you can do this at home at your leisure time period when you like to, which will be fun anyway. Okay, so this is the last talk of the day. It will be a little interesting because I plan this talk to be the second talk of the day about cosmological probes for large LSST, and it will be a little bit easier now because you already went through all the lectures today. So today's outlines is going to be quite rushed, and I'm going to concentrate mostly on baryon acoustic oscillations because that's my expertise. And I'll be trying to go through a bunch of other things, such as the supernova and weak lensing and a little bit of strong lensing. But there are a lot others I won't have time to cover, such as cluster counts and anything like you can come up with cross-correlation with different probes with each other. And I apologize in advance for that. Before I go on, I have to remember to thank Martin White and Rachel Manaman for using some of their lecture notes for things I don't have. And here we go. So we see and probe dark energy through cosmological probes using basically a few directions, right? One is what you heard of as standard candle. We measure DL, which is an integral of H inverse, or standard rulers, which we measure dA, which is the angular diameter distance, or growth of fluctuations, which is testing the extra components of the density of the universe versus modified gravity. So these three things are actually pretty easy to really think of what probes dark energy. And for those who probably have seen this earlier on already, the Hubble constant can be basically written as, well, actually this is a very good, useful equation to look at, which is basically sum of all the components in the universe. This is better, okay. And for standard ruler, suppose that we had an object whose length in meters, like actual physical meters, that we knew as a function of cosmic epoch. And by measuring the angle delta theta subtended by this ruler, and this ruler has a physical distance, right? So if this right here versus right up at your face, they actually subtend different angle, you can actually see that you can look at this equation very easily and look at the subtended angle, which is the physical distance divided by the angular diameter distance, basically from us to the ruler itself. And the angular diameter distance is basically an integral of 1 over h. And you can see that you have the luminosity distance that people all have told you about, which is this, what supernova also measure. All these things basically says, if you have a standard ruler, and you can measure the redshift interval of associated with different rulers at different distances, we can map out the Hubble parameter using this particular equation. David Haas distance measures in cosmology is a very useful references for people who are starting on this one. So this is an easy way to do standard rulers. So what are the ideal properties of standard rulers? Like, what are the things we're looking at if you're a cosmologist, right? To get competitive constraints on dark energy, you need to see things changing in the Hubble parameter at about 1%, which gives you about 10% in dark energy equation of state, which is kind of what you want. And you can change this error accordingly. If you want to have a stringent dark energy equation of states like 1%, then you actually have to change the Hubble parameter by a very, very tiny level. You have to detect at this level confidently. And we need to be able to calibrate the ruler very carefully and accurately over most of the age of the universe. As we talked about, we have to do it at intervals of redshift. So you want to have this calibrated over a whole range of the universe age. And you need to be able to measure this ruler over basically the whole volume, or most of the volume of the universe. And want to be able to make extra precise measurements of the ruler. So all these properties are very important to look at what are good standard rulers. So where do we find such rulers, right? Individual probes could maybe never uniform enough, maybe. Maybe we'll find something different and you can prove me wrong. And so we were thinking about using statistics of large-scale structure of matter and radiation, things that are really large number. We're doing statistics here. So it's much easier in some sense to be able to stick with earlier times and large scales. Perturbative treatment of the universe will still be valid. So we actually can trust the physics, that the calculations we do will be very much under control. And the preferred length scales arrive from the physics of early universe that imprinted on the distribution of matter or radiation are preferred here because these are things that we actually can calculate. And you'll see that these are the particular papers I refer you to read if you like about what I'm about to introduce to you, Baryon acoustic oscillations. So what is this? You've probably heard all these stories before, but let me just remind you, these are basically the sound wave at the very early universe, that's 1 in 10 to the 5, that grow into order unity fluctuations today. And dark energy changed the apparent size of this ruler. And that's basically the game here. And why is it going, what is this happening? Do we have this standard ruler? Basically, very early on, we have all the matter all come together. We have the photons, electrons completely coupled with each other because of the high temperature, and they basically interacting very heavily, tightly coupled. And then as the temperature drops, while the photons and the electrons actually getting pushed out by the photons' radiation pressure all the way outwards. So let me just do this simulation again. Photons and radiation get pushed out all the way outwards. Temperature keeps dropping. Once the temperature drops to a certain point, it basically gets so cold that the electrons and the photons stops being coupled to each other. And the radiation free streamed while the electron stays fixed. Electrons had dragged on all the other baryons along the whole way because it's electrostatic equation. You can all check this out. And you will see that there's a ring here. But since the universe is not just one particular perturbation, there are many, many perturbations at the very early universe, such as in this diagram here. And so every one of them will have a little length scale about 470 million light years large. And this is the ruler we're talking about, 470 million light years long. And people use this word like 150 megaparsec. It's slightly different now, but basically the idea is that you have this ginormous ruler out there, and you can use this as the standard ruler for you to measure. We're working in large scales, so we can probably avoid all the possibly nonlinear physics, very messy ones. And its physics are determined at very early times. So that's a good thing because perturbation theory is probably still valid and under control. So nature has supplied us with a distinctive feature of well-known intrinsic size. We can measure the distance to a sample by measuring the angular size of this feature. So this is the poor observer if we don't have any support from NSF or DOE or any other agency. And we're looking at all the different epochs of the universe from basically the CMB, which has the first BAO when you think about it, and then all the way to different epoch. And this grows as the universe expands. And you can see it's subtended at different angle for the observer. And that's what we're trying to map the universe cosmic history by mapping these BAO scales out there. Yes?
The instruction for the orange shows that you're not in the totally non-perturbative.
Which we'll come to very soon. That's why I'm actually going to go to the pesky details in about 5 slides. So I want to go into some equations here. The cartoon at early times, the universe was hot, dense, and ionized. Photon and matter are tightly coupled by quantum scattering. And the short mean-free path allows basically a fluid approximation. Everything is just a fluid. And initial fluctuations in density and the gravitational potential drives the acoustic waves in the fluid with compressions and variations here. So this is the equation you actually solve. I'll just point out specifically the effective mass here is a function of the baryon to the matter, to the radiation, sorry. And this is what determines basically some of the most important features that we're measuring nowadays. And this is the baryon, delta baryon, how it changes in time as an actual co-moving time. And this shows up as the temperature fluctuations in the CMB. And you can solve this equation fairly easily if you think of it, because you've seen this before, and it's a sort of simple harmonic oscillator. The first compression is actually at the first peak here is the density maximum and velocity no. And then you actually can see this is a rarefaction peak, which is right here at the second peak. And the velocity maximum is at this trough. The acoustic scale is actually set by the sound horizon at the last scattering surface. S is Basically, just the sound horizon times the time to the last scattering surface, which has an integral. So this is the integral I was trying to say here. Sorry, which one? This is CMB. This is not VOS at all. This is very early. This is at redshift 1100. For those who are wondering, they are the same bearing. I mean, they are the same acoustic waves. Exactly. One is imprinted on the radiation. The other one imprinted on the baryons. That's the only difference. The physics are the same. So what is this sound horizon here? It depends on the epoch, the recombination. Basically, at what time do you integrate all the way to the expansion of the universe? As you can see, this is the H again, which is H inverse, very important. The baryon to photon ratio through the sound speed, which is right here. The photon density is known exquisitely well thanks to the CMB spectrum nowadays. And you have this actually tied down very, very well right now with such an accuracy that Planck has provided us, so we can actually use this as a very accurately calibrated standard ruler. So since baryons contribute only 15% of the total matter density, the total gravitational potential is affected by the acoustic oscillations with a scale set by S. But since you're only 15%, this is leading to a very small oscillation in the matter power spectrum P of K. And this is suppressed by basically the baryon to total matter fraction. And that's why it's actually much, much less obvious. While the radiation has such an obvious oscillation, the matter here is basically suppressed by the baryon to matter fraction. Does that make sense? And if you divide out the growth trend, you can see a damped harmonic sequence of wiggles in the power spectrum of the mass perturbations of the amplitude. And it's about order of 10% on these very, very big wiggles. But you actually don't easily see that, all of them, because this is not a very simple CMB experiment. Well, I shouldn't say simple. This is not a CMB experiment where we have such strong signal to noise. We're actually still at the area where the signal to noise is not as strong as to seeing, the seventh peak or something like that. And there are higher order effects, such as the matter and the radiation oscillations are not in phase. The phase shifts depends on K. I'll probably start wondering, who can tell me why that's the case? There's a subtle shift in the oscillations with K due to the fact that the universe is expanding and becoming more matter-dominated. The finite durations are decoupling, because when they're decoupling, they don't do it all at once, right? So the last scattering surface is not an infinitely thin slice. That actually means the photons can diffuse out of the overdense density smaller than a certain scale, leading to a damping of the oscillations in the small scales. But regardless, the spectrum is very much calculable, and S can be inferred very easily. So these interesting oscillatory features are frozen into the mass power spectrum, and providing a known length scale can be measured as a function of Z. So let's pause a little bit here. Questions? No questions? I'll start asking questions otherwise. Yeah, okay, so do anyone want to explain why there's a shift in phase between the CMB and the BAO? You can talk to the neighbor. Okay, take 1 minute. Talk to your neighbor and see who'll come up with the answer quickly. Yes, actually, I will show you the shift. This is the talk to your neighbor 2 minutes discussion. Hi, everyone. All right. I know there are more discussions out there. I've heard multiple very good directions in terms of the answers. Do we have some volunteers to tell us what they think is happening? Yes?
I think this is wrong. So when the wave is traveling, the photons and electrons are coupled and they're dragging the baryons with them. And then when you get to about 1100, then the protons and electrons recombine, and the electrons and the photons start free streaming away. So they start first. So they have a smaller angular scale on the sky when you look at the temperature shift when you come up. And then the matter keeps going a little bit until all the photons are gone, and then it freezes, which gives you a difference in the scale of the size.
That's a good one. But I mean, some of it is very correct, and I just don't know if that's the only reason. There are other reasons of the shift. I mean, there are multiple reasons for the shift. Yes?
We were saying that the photons can free stream away as soon as density is low enough in the universe that the perturbation knows about itself and can start oscillating. Photons free stream away. They can drag electrons with them via Compton scattering, but dark matter, which was still maybe in this fluctuation, doesn't interact with the photons, so it doesn't get pulled away by photons as they leave the perturbation. So the dark matter particles have sort of a drag effect on electrons, on baryons matter, that would be otherwise just following the photons one-to-one via Compton scattering.
Okay, so there's some really good bits, and then there's some part that we might want to clarify. So when actually when it was going further, right? When at the very beginning, like we had this. I just want to explain this because I think it's important that we get this right. So when this happens at the very beginning for each perturbation, the photons and the baryons get dragged. I mean, we're going out together at the same time because of inverse quantum scattering. They couple together. But once they're not coupled, at this time, the electrons were actually being dragged out by the photons, right? But once the photons go, the electrons actually stay put. So they're not dragged out. Is that what you said, actually? I just want to make sure. Okay. But then the dark matter is a little slower, but they're still interacting gravitationally with the baryons. Is that correct? Okay, so I think I understand what you're saying. I think that was actually fairly close to what I expect in terms of the answer. So then they actually take some time to respond and actually drag back the baryons a little bit. Is that what you're saying? Okay, I think that's very close to the, I think, full answer. Is there any other things that's also important to this process? Yes?
So there's a 180-degree sign flip in the CMB compared to the matter because the dense region actually corresponds to a dip in the CMB spectrum because it's a redshift of photons.
You have to speak louder. Sorry, I can't hear you.
The whole thing? I said that like so there's a sign flip in going from the CMB, the matter to the CMB spectrum because the photons, the CMB hotspot corresponds to a less dense region because the photons have to climb out of the potential well in a dense region, and that redshift can end up looking the other direction as you would expect.
So you're just talking about the density over density difference, basically, in CMB. And that's also important, yes. Anything else?
It looks like there's kind of a frequency jump.
Can you go back?
Where there's twice as many CMB peaks as matter density peaks. Right? The wavelength on the matter oscillations is double the wavelength on the radiation.
Not really.
Well, it's not
There's some.
No, because if you look with the second and third, it's a half cycle in matter, and it's a full cycle in radiation.
They were dragged out further out, basically.
It's not a phase shift, it's a different wavelength.
No, they phase shift. But we can definitely talk more about the specific, whether it's actually doubling or not. Okay, well, I think that answer and this was fairly close to what we actually want. And also there is we have to think about the fact that we do have the fact the universe is expanding and has more and more matter, becoming more and more matter dominant. That also adds to the slight phase shift.
Could you summarize concisely the answer?
Actually, I was hoping to go to a slide on it. Is that okay? But yes, so basically, actually, from the beginning, let's start from your part and her part. So we have the photons and the baryons actually talking, coupling to each other, and then we have inverse quantum scattering, basically having them together. And then it goes further out because of the radiation pressure. And once you do that, the temperature drop at some point to cold enough that it's actually not interacting with the photons, and the baryons are not interacting with each other via the quantum scattering, inverse quantum scattering. And then at that point, free screaming happens. The photons go out, and the matter go at slightly different speed. But remember at that point, also from her point, which is very important, that the matter was actually kind of dragged on a little slower by the baryons through the gravity. So there are multiple things happening, given the speed is also different from propagation, and the fact that it's slightly slower. Does that make sense? And then in addition to that, there is the fact that the universe is expanding itself, and it becomes more and more matter dominated. So all these effects add on to each other to change the phase. Okay, it's very many things. But I think we should talk about, I don't think there's a doubling of phase, but I can check. Sorry, where? Oh, the vertical scaling. That one, David likes to talk about it. This one.
Right. So that looks like it's a pretty high contrast. Like peak to the central peak to satellite.
Yeah, but this is an animation. So we had that discussion before in the Boss mailing list. This is not exactly the right representation in your head that you should have. And I think we have made multiple different movies for this. And I think David made one of them. Did you make one of them? That was a better representation of this. It just happens I have this for myself. So if you want better movies, David has another one. That was pretty cool. I would like to move on a little bit, if that's okay. I'm going slightly behind in my schedule. Cool. Okay, we're here. So dark energy or early universe weirdness, right? So key to computing as this time horizon is our ability to model the CMB anisotropies. So we want to be sure we won't make a mistake in our understanding at 1,000, 1,100 for the property of the dark energies. So what could go wrong in the early universe modeling? That's something actually people don't talk about very much because we just assume the stuff that they gave us from Planck team or WMAP team is correct. So, but how do you interpret it is actually important. So recombination has to be done exactly correctly. If you misestimate the ratio of the baryons to photons actually matters because you misestimate the sound speed. If you misestimate the Hubble parameter at very high redshift, that also matters. If you miss the radiation in your calculation. If you have strange thermal history, such as decaying neutrinos, that also change what you should calculate for the time horizon. And if there's isocurvature perturbations, that also matters in the end. But it seems future actually current CMB anisotropies constrain S really well, and they have actually put in all these different possibilities in their analysis. For example, I think the recombination is made exquisitely correctly these days. And I think this should constrain S enough for the measurement of the BAO, even in the presence of very odd high C physics. So this is the part people don't really tell you about. You have to calibrate BAO to sound horizon. If you don't get sound horizon right, you won't get the BAO right. Okay. As to discuss unit, okay, this is only 2 minutes this time. Let's not go on forever. What are the possible problems of BAO? 2 minutes. I'm starting to count this time. Otherwise, we'll go forever. Systematic errors, observational errors, theoretical errors, anything. Proper motions. Wow, that's hard. Okay, 90 seconds left. So I'll call on one volunteer to answer the question of what are the possible problems of BAO in about 30 seconds. All right, everyone, we need one volunteer for possible problems of BAO. Otherwise, I'll randomly call on the last name. Yes. When you say redshift space distortions, what do you mean exactly? Very good, very good. We're measuring the redshift space, not the real space correlation function.
And then the other one, I think RST is much more under control, like the fact that structure formation becomes nonlinear, and this nonlinearity distorts the spectrum and shifts a little bit the value one computes for the length scale.
Yes, but people did look at that. That one we actually looked at is about 1%. It's less than 1% effect. So the extra shift on BAO because of nonlinearity is a very small effect, and it's under control. But that's a good one. That's a very good one. People actually wrote papers on this.
The main exchange adjunction and union this collaboration has shown using their own simulation that it is not negligible. This nonlinearity if you take it into account.
Very good.
Maybe it's my misunderstanding, but I thought the redshift space distortion isn't that we're measuring in red space, it's that we're not really seeing the proper Z, because if it's in some gravitational structure, it might be falling in or moving out, which distorts the
So I think they meant that we're measuring in redshift space, not that it's redshift space distortions. In the way people actually talk about measuring F sigma 8 from redshift space distortions, I think he just meant we're measuring redshift space, not real space correlation function. I think that's what they meant.
my understanding right, what I just said.
I think about redshift space distortions, I took out those two slides because we're actually not going to be able to measure it that well in LSST, but we can talk about it later. Cool. BAO in configuration space, very quickly, why people want to do that? Because in configuration space offers some important insights that might be useful when we consider things like nonlinearities and bias that I was trying to prompt from the audience here. In configuration space, we don't measure Pao spectra, but correlation functions. And the harmonic sequence will be a delta function in R, and the shift in frequency and diffusion damping broadens the feature. That's why it's not so sharp anymore. It's just a very broad-ish acoustic feature at about 100 megaparsec over H, with a width about 10 megaparsec over H. And so what are we waiting for, right? So we now think we should just measure in correlation space because it's one peak, so it's easy to locate possibly. So what we usually do here is find a tracer of the mass density field and compute its two-point correlation function. We locate the feature, because it's easy to locate one little bump, in about corresponding to the sound horizon S. And then you measure the subtended angle, the differences in subtended angle and delta C subtended by the sound horizon S at a variety of redshifts. So you want to do it in multiple redshifts. And you can compare it to the value at redshift 1100, which is what the CMB measured, to get dA and H of C, dA being angular and diameter distance, H being the Hubble parameter. And then you can infer the expansion history, dark energy properties, and modify gravity if you don't like dark energy. But there are all these pesky details, right? So I was trying to prompt this. We measured the nonlinear galaxy Pao spectrum in redshift space, while we actually don't have a turnkey method to go to linear, real space, matter Pao spectrum. So that was actually a big deal. So how do we handle this, right? We don't have a turnkey method to reliably go from the measured galaxy positions to sound horizon constraints. So it's fairly hard to propagate systematics, how to do trade-off studies, and how to investigate sample selection effects. And since BAO surveys are always in sample variance-dominated regime, we can afford to take a huge hit in theoretical systematics. So people dive in and try to figure out all these pesky details. people do numerical simulations. I think in the back they just mentioned someone has, I think Jean-Michel has done some simulations, and a lot of people have done it too, to simulate the dark matter, simulating dark matter boxes for BAO. That was done, the earliest one is actually 1999. I was surprised about this when I saw this. They actually started in 1999 for simulations. Back then, 10 to 6 particles, very small number for the people doing simulations nowadays. Sprinkle et al. 2005 is 10 to 10 particles, 10 to 4 dynamic range, 0.1 gigaparsec cube. Just to mention now what we usually use, a box is 2 gigaparsec on the side, particles is 4096 cube, which is much larger number than these number of particles. And also our understanding of galaxy formation has increased dramatically. So you can go from dark matter to galaxies, hopefully in some ways. And we're trying to learn what range of behaviors we see in these simulations, what kind of galaxy prescriptions works best, and how do we parameterize these effects? And can we gain analytical understanding, or are there shortcuts for these complexities? There's Lagrangian displacement distribution from Eisenstein, Stoll, and White 2007. And can we push it further using something called reconstruction that someone actually brought up earlier? And I'll go into this a little bit. So what is this reconstruction thing that people talked about, and why do we need this? Why do we need this is because as larger structure grows, the neighboring objects pull on the baryon shell around any point. So this superclustering causes a broadening of the peak. Basically, everything tugs on that peak, right? So this little shell gets tugged everywhere. And it makes it broader. And that's why actually people have been trying to model this by using various different ways, such as, say, creating a template for the low redshift Pao spectrum. You can use this particular template if you like, or doing a template in a configuration space. Or we can try to do something like going back in time, which is reconstruction here. And let me show you how this is done. So basically, this is the BAO peak at, well, this is at redshift 49, the black line. But at redshift 0.3, it's much smoother out, completely smooth out. The usual peak you see is usually multiplied by r squared, so it's completely exaggerated. This is like what you actually expect, a slight bump. And what people are trying to do is to make it go backwards in time to the reconstructed one, which is the dashed orange line here. And so if we can do that properly in controlling all the systematics, we might be able to gain a lot without actually building another experiment or surveying more sky. So how do we do that? Let's pause. Everyone knows about reconstruction? Already? No? Yeah? Well, you can also just read this, but actually, quick question. How would you do going back in time in cosmological simulations? If I just ask you this question, as a physicist, you'll think, what do you do? I measure all these galaxies. I measure some correlation function. I have this very, very flat bump. I want to make it sharper, right? So how do I go back in time or infer what do you do? What do you do going back in time? Velocity field, that's good. How do you get the velocity field? Because we don't measure the velocity field. Redshift, but then the redshift is individual object at that point. It doesn't actually give you the velocity of individual object, right? So you want to know what this galaxy is supposed to have gone through, so you can move it backwards. But that's a good one.
Does it depend a lot on how far back you want to go?
Well, the further back, the better in some ways, right? But I don't know how far we can go.
For a small amount, you can make linear assumptions, and for a large amount, rewinding an n-body simulation is, I would assume, impossible, or
Right.
at least intractable.
Very, very hard. So that's exactly what people do, actually. This is the slide we're talking about. We're using the observations to undo the nonlinearity. You measure delta x, which is the over-density field. You infer the potential. You calculate displacement, which is basically the velocity field. Thank you, in the back. And once you do that, you have the velocity or the displacement. You move the galaxies backward by just linear theory. So people have been working on including first order, second order perturbation theory to try to even push even further than linear theory. But so far, we've been doing it with linear theory. And we move the galaxies back to us as far back as we can. But basically, we just do it as much as we can without introducing systematics. So that's what we're actually going for. And putting the information from the phases back to the power spectrum. There are many, many ideas people trying to do this, measuring velocities back in the 80s and 90s, but not much of this actually has been tried since for reconstructing BAO, for example. So that's very good interactions just now. Thank you, everyone. So musings on nonlinearity. Some more discussion about what statistics you will use to measure BAO, right? You can think about it in Fourier space. You have excess power in small scales. You have mole coupling. If you have any survey geometry, you'll have mole coupling that erases the oscillations at high Fourier scale, K. And you also have nonlinearities appear to encroach on the signal, and you're unclear whether the acoustic scale is shifted. That's pretty hard in Fourier space, but we have done some of that. Configuration space. Nonlinearity smeared initial peak by about 10 megaparsec. The smearing decreases the signal to noise, but we can do that. We can remove this by doing reconstruction. And you might have a bias and a shift in the peak position, but you can estimate that by looking into simulations at the minimum. So there are a lot of different things you could do, but none of them are actually completely perfect. The hardest issue is something called the galaxy bias. I think a lot of people might have heard of galaxy bias here compared to reconstruction. The galaxies don't fully trace the mass very fully, but galaxy formation scale is way smaller than 100 megaparsec. So the effects are hopefully very smooth. So people are investigating these effects. These are the list of older papers, but very classic papers, to see how you actually affect the BAO by looking at the galaxy bias. And it turns out that most of different galaxy bias, you can put different bias population together, you can measure BAO, and it still be not biased. And you can have basically just model it by a linear bias model, and it will be perfectly fine for just measuring that one scale. So maybe the standard ruler is okay. We're gonna skip this, unfortunately, but I could actually send you guys challenges tonight. There is some technical problems on this one, unfortunately. It will be really fun because there are 11 questions on BAO and weak lensing and cluster on it, but I cannot send you challenges until they fix it because there's too many people signing up at the same time. Let's apologize for that one. So that gives us more time to move on to supernova and lensing, which are not my expertise, so hopefully people will chime in for those who actually know more than I do, please. Type 1a supernova properties. We need the spectral properties as a function of time, which are basically consistent over different supernova. That was a story. They actually stand a candle. The light curves have similar general shape for every single one of them, and the variations of the shape correlate with the luminosity, and it depends on the wavelength, and it relates to various amounts of radioactive Ni, which is nickel, I think, from progenitor explosion. So this is basically the story about supernova. And I would like to have people think about what are the possible problems of supernova for the next 2 minutes. I'm going to start counting now. Many or zero problems? What? I mean, I'm done with the BO. If I go further, it will be quite a lot of pesky details. In a couple minutes. Actually, after this. 30 seconds. Any thought? Okay. All right. All right, everyone. Do we have one volunteer? One volunteer to tell us problems of supernova. I hope Saul is not going to be here to tell me I'm wrong. Yes, Jim.
Photometric calibration. So they need to be able to say that the survey that they, the supernova that they observed a long time ago that was nearby using some entirely different telescope, they need to compute the ratio of that flux to the supernova they just observed with a brand new fancy telescope, and they need to not have any bias in that ratio of fluxes. Otherwise, that error will directly mess up how far away that they think the supernova actually is.
Very good one. That's a very important one. Any other ones? Yes.
Well, this correlation of shape to luminosity that we use to calibrate light and redshift.
Very good. I think the expert's nodding. I'm just listening to him. Yes.
So there's kind of a whole list of issues you have to deal with. One of which is dust, the properties of dust evolving as a function of redshift.
Gray dust.
No,
I'm kidding.
gray dust aside, yeah, gray dust is cool, but, and then do the light curve shape evolve with redshift. We don't really know what the progenitor system is at some really deep fundamental level. We know it's a carbon-oxygen white dwarf, but we don't know if it's a one solar mass white dwarf that always explodes or if it's a Chandrasekhar mass. There's kind of the party line that it's a 1.4 Chandrasekhar mass white dwarf, but there's a lot of evidence that that's not necessarily the case for all of 1A. There's also the issue we don't know what the donor star is, so we don't know if it's a massive star that's giving, or a red giant anyway, not a massive star, but a red giant donating mass and donating hydrogen, or if it's two white dwarfs that crash into each other. And so
You know way more than I do at this point. I'm going to delegate to him to say whether your answer is correct or not. I know him from Berkeley.
Just this and the demographics of supernovae, evolution of the demographics.
Okay. So